Now let us look at the next topic, which is related to inter-process communication. The topic is inter-process communication. Inter-process communication. Okay, so what do you actually mean by inter-process communication? See, whenever in your operating system, if you have an operating system, the responsibility of operating system is to provide an environment. So assuming that this is your operating system, this is denoting your operating system. Now in your operating system you may be having multiple processes, like this may be a process, it may be a process, it may be a process, you may be having multiple processes. Okay, so this is the process, this is a process P1, this is a process P2, process P3, process P4, process P5, P6, P7, and so on. Now these processes may want to communicate with each other. Now when they want to communicate with each other, that means sometimes what can happen is they can share some data variables, they can share some data members, and it may happen that they may also share some kind of resources. Now these resources can be anything. Generally whenever we discuss about resources, also resources can be, for example, you have main memory, maybe you're having a printer as a resource or some data variable as a resource, right? For just for example, let us assume you are going to buy a phone on Flipkart. Okay, you assume this is a website, this is your Flipkart website. Okay, Flipkart website, and there's a different phones which are listed on this website. This is one phone, this is second phone, this is third phone, and fourth phone, and so on. There are different phones, mobile phones, which are listed on the website. And assume this is iPhone something, iPhone 6, this is iPhone 5, this is iPhone 4, this is iPhone 7, and so on. These are different phones, and there's some, number quantity of these phones. This is around 59 phones are there, this is 48 phones are there, this is 31 phones are there, 28 phones and 12 phones, and so there are different capacity, different quantities of these phones. This is denoting the quantities of these phones. Okay, now assume there are 2 or 3 people who are trying to buy a phone. Maybe this is iPhone 6, they're trying to buy the iPhone 6. A person came whose name is, assume, Rakesh. Rakesh is trying to buy this phone. There's a person who is Suresh. Suresh is also trying to buy this phone. There's a girl whose name is, assume, Bhumika. Bhumika is also trying to buy this phone, and so on. So these people are trying to buy the same phone. Now if they are trying to buy the same phone, then it can happen that it may create some kind of complications while they are doing it. Okay, when I'm saying complications, it is because this phone, this will be kind of a shared resource or a shared variable for all of them. Let me tell you what is actually a shared variable or shared resource. Assuming that if you have some statements, for example, if you have a programming statement like this is your main function, and somewhere in the program you have a statement like phone quantity is equal to phone quantity minus 1. This is a variable. This is, for example, if Rakesh is going to buy this phone, then he's going to make the phone quantity is equal to phone quantity minus 1, so he's going to reduce the quantity to 58 and so on. So these people can reduce the quantities. Now if you look at this instruction, then these instructions are generally, when you execute the program, there are different phases in the program execution that you already know, that we already discussed. They are, initially, if you have a high level program, now this high level program is generally given to a preprocessor. Then this preprocessor gives a pure high level language program, and then this pure high level language program is given to a compiler, and this compiler gives you assembly code, and this assembly code is generally given to an assembler, right? So when this compiler is giving this kind of assembly code, these assembly codes are generally given in like add r0, r1, or subtract something, right? These are kind of machine languages, or you can say assembly language. So in the same way, if this instruction is going to be executed, then what will happen? This instruction is generally broken down into 3 instructions. For example, the first instruction can be load the value of phone variable into the variable R0. That is, you are going to load this register, this value to the register R0. Then you are going to do add R0 comma hash1, that immediate value, and then you are going to do store phq comma the value of R0. So generally every instruction like this, these kinds of instruction are broken into 3 steps. Number 1 is the read step, second one is the write step, right, and third one is the commit step, right. So commit is generally, that means you are trying to make the changes permanently, right. So, or you can say read or write, these it can be broken into 3 steps like this. Okay, now what can happen, assuming that 2 people are trying to buy the same iPhone parallelly. So like this is the quantity of the phone, this is denoting the quantity of the phone, and assuming the current quantity is 58, and these 2 people are Rakesh and Suresh. Rakesh and Suresh both want to buy the phone. Now if they are going to execute these statements, that means they have to execute these 3 specific statements: load, add and store. So that is read, update and write. You can also write it like read, update and write commands. So they can also commit it like this: read, update and write commands. So what will happen, first assume Rakesh and Suresh both came parallelly, they are working parallelly, and now Rakesh, first of all Rakesh is going to read the value of this, assume this is a variable q, so read the value of q. So Rakesh in his variable he is going to say that the quantity of the phone is 58. Then assuming there is a preemption, if they are working parallelly, see, first of all, why do we actually want to work parallelly, is because we want to increase the throughput of the system. We want to increase the number of statements which are being executed per unit time. We want to increase that. So if Rakesh wants to buy this phone, then initially the Rakesh has to buy get this phone. You can say Rakesh has to read the value, then Suresh will come, and Suresh, assuming Suresh is also going to read the value, so Suresh is also reading that there are 58 mobile phones are left. Now this 58 and 58 values, they will be stored in their local register, that is R0 is going to be 58, and here also R0 is going to be 58. Now what will happen, Rakesh will say I'm going to update the value of R0, so R0 is equal to R0 plus 1, right. That means I'm going to update this value, that I still remember that Rakesh has not written the value, and then there is a preemption, because at one time only processor can execute only one instruction. There is a preemption, and again Suresh came, and Suresh is going to update the value, assuming his variable is R1, so it is going to do R1 is equal to R1 minus 1, sorry, it is subtraction, or I should have written, instead of addition I should have written subtract R0 comma hash 1, so I should have written like this. So he's going to do R0 minus 1. Okay, so they are updating the values, and after that again there is a preemption, and then Rakesh is going to commit the value, or he's going to write the value of R0 variable onto this. So he's going to see, so I've seen 58 mobile phones, I'm going to buy one, so I'm going to make it 57. So as soon as he is writing this, so he'll make it 57, and again there is a preemption. And after the preemption, Suresh came, and Suresh is also trying to write the value of this variable. He also said that I've seen that there are 58 mobile phones. I'm going to subtract 1, and so I'm going to write it. So he's again going to write 57. Now you see what has happened. Rakesh and Suresh both bought the same phone. Rakesh also bought the iPhone 6, and Suresh also bought the iPhone 6. They both have seen that there are 58 mobile phones, but after buying 2 mobile phones, the value should be 56, but here the value is only 57. Why? Because they are executing or updating parallelly, and during parallel execution there can be a preemption. So that means it may happen one statement is Rakesh is executing one statement, then your scheduling algorithm try to decide that Suresh should execute next statement, then your scheduling algorithm is giving CPU to the Rakesh, then scheduling algorithm is giving CPU to Suresh, then scheduling algorithm is giving CPU to Rakesh, and again Suresh. Now because of this, what has happened is the value which is written by Rakesh is lost. And Rakesh has written that I'm updating the value as 57, but Suresh is also writing the value 57. So instead of value 56, they are writing only 57. And because of this, one phone went missing, because the company Flipkart will think that where we must be having some problem, maybe some no, we may be having some thief in our unit. So but still no one has theft anything. Rakesh and Suresh both paid the price, they both bought the phone, but still in the account they are showing that there are 57 phones left, but ideally there should be 56 phones. Okay, if it is complicated, let me explain it to you in one more fashion. There's one more way of explaining this thing. Assume there are two people who are working parallelly. Number one is the person named Himanshu, and second one is a person named Tarun, right? And Himanshu and Tarun both are brothers, and there is an account which they have a common account. Assuming this account is having around 10,000 rupees. Okay, now what is happening is Himanshu is earning and Tarun is spending some money. Himanshu is trying to add plus 5,000 in the account, and Tarun is trying to spend 5,000 from the account. Okay, now what will happen? This is the account. First of all, assuming that Himanshu came and Himanshu is reading the value of the account. Then Himanshu is reading, so Himanshu is going to say, yes, that I read the value, so the money saved in the account is 10,000. So Himanshu is going to read 10,000. Then again Tarun came, and Tarun, the CPU, see how Tarun and Himanshu are coming. Assuming this is the CPU, Tarun is standing in a shop and he's buying something, and Himanshu is in the bank and he's trying to deposit something. Both of them are assuming working parallelly. And when they are working parallelly, if they are working parallelly, now this CPU can only be given to one process at a time. So Tarun is acting as a process, Himanshu is acting as a process. The CPU can only be given to one process at a time. So if Tarun is inside the CPU, then Himanshu cannot be inside the CPU. If Himanshu is inside the CPU, then Tarun cannot be inside the CPU. So we have to take this process out of the CPU to give CPU to another process. Right, so here you can see, first of all, CPU is given to Himanshu. Then assuming that CPU is given to Tarun, so Tarun is also going to read the value of the account. And then after reading the value of the account, again CPU is given to Himanshu. So Himanshu is doing whatever the value of account is equal to account plus 5,000. Remember, he is not writing the value, he is just calculating on his end. Now CPU is given to Tarun. Now Tarun is doing account is equal to account minus 5,000. Now assuming that CPU is given to Himanshu, see at this moment, but either CPU can be given to Himanshu or Tarun, any one of them. So assuming Himanshu is going to write the value of account, he's going to see that I've seen 10,000, I'm adding 10,000 and I'm writing the value of this account, this value to the account. So he's updating this 10,000 to 15,000. Right, and as soon as Himanshu has returned, so CPU is given to Tarun, and Tarun has seen that account was having 10,000, I spent 10,000. He's going to write that account should now have 5,000, so he's also updating this value to make it 5,000. Now what has happened? Because both of them are accessing the same data variable at the same time, still there is some kind of problem, and this problem is creating an issue which is inconsistency in this account number, right? And this inconsistency is because both of them are trying to have a race, or you can say it is a kind of a race condition. Both of them are trying to have a race. The one who is going to update later, that value will be written in the account. For example, if instead of Tarun, if Himanshu had written the value at a later point of time, then this value must have been written on the account. So the one who is going to update later, that value will be saved on the account. So this problem is arising because both of them are accessing the account at the same time, right? And both of them are trying to update the account at the same time, and there's a condition called race condition. Now if we want that only one person should access the account at one time, two or more than two persons should not be allowed to access the account, so that we can guarantee mutual exclusion. Mutual exclusion means that no two processes may be simultaneously present inside the account at any point of time, or you can say two processes should not be present inside the account at any point of time. Only one process is allowed to access the account at one time. Okay, so this is your basic need of synchronization. Now this synchronization, let us introduce ourselves with some basic terminologies which we require. Number one is, the first terminology which we need is, what is a critical section? What is a critical section? What is a critical section? So you can say the portion of the program or text where the shared resource or the shared variable is placed is called as critical section. Let me write it down. It is the portion of the program, the portion of program text where the shared resource, or the shared variables will be placed is called as a critical section, right? Next definition is a non-critical section. Non-critical section. What is a non-critical section? You can say a non-critical section is the portion of the program, is a portion of program text which is independent of respective processes, right? And the third definition which we needed it is the definition of race condition. So what exactly is a race condition? Is the condition in which the output of the program depends on the execution sequence of statements. That is called as the race condition. So let me explain it like this way. So assuming in a program we'll be having different sections. The first section is called as non-critical section. The next section is called as a critical section, and here this section is again there's a section which is non-critical section. So we are having three sections. Number one is non-critical section, second one is the critical section, a third one is again non-critical section. Now what is this critical section? This section is a section of the program which is containing the shared variable. For example, in the examples which were already taken, the one example was related to bank and an account. In that particular account is a critical section because we should not allow two or more than two people to access the account simultaneously, right? In the same way, when we talk about the Flipkart website, now the quantity of a product is a critical section, because when two people are buying the same product, then we should not allow both of them to update or work on the same data resource at the same time. In the same way, if you discuss the example of a railway reservation system, now what should happen is, if two people are trying to buy a ticket, or you can say the same seat should not be allocated to two people at the same time or simultaneously, right? So this way you can see there's a non-critical section, there's a critical section, and again a non-critical section. Non-critical section is a section of the program where there are no shared resource, or you can say no shared data variables, And critical section is a section of the program where there is no shared, in case of critical section is a section of the program which contains a shared resource or shared data variable that two or more processes may try to access simultaneously or may try to access at the same time. Okay, so in this chapter of synchronization, we'll try to study what are the different problems which you can face while if two processes are trying to access a critical section at the same time. At the same time, we'll try to give different mechanisms to not allow different processes to access the critical section at the same time, or you can say to maintain the mutual exclusion. Now there's one more set of terminologies which you need to study for any process, to achieve synchronization. See, this is called as synchronization. Synchronization means the critical section should not be we should not allow two or more processes to access the critical section at the same time, or to work on the critical section at the same time. For that purposes, we are going to do something called a synchronization, and synchronization is going to ensure or make sure that they should not access them at the same time. So to achieve synchronization, we have four conditions. Which should be met, and these conditions are: number one, out of these four conditions, two conditions are primary conditions. Out of these four conditions, two conditions are primary conditions which should be met, and two conditions are secondary conditions. What are the primary conditions? So first primary condition is we should be able to maintain mutual exclusion. And second condition is we should be able to maintain progress. And what are the secondary conditions? So secondary conditions are: number one, we should be able to maintain bounded weighting. And number four, we should this is number three, and number four is it should be architectural neutral, or architecture neutrality. Okay, so what is this mutual exclusion? Mutual exclusion is two processes may be simultaneously present inside the critical section at any point of time. Right? For example, if you have, this is the critical section. Now inside this critical section, two processes should not be present at the same time. This should not happen. We should allow only one process to enter inside the critical section at one time. Two processes or two or more processes should not enter in the critical section at the same time. Okay, write this definition. Okay, these definitions are important. Second, what is a progress? Progress is no process which is running outside the critical section should block the other interested process from entering into the critical section when critical section is free. What do I mean to say is, if assuming that this is a critical section and there are 4 or 5 different processes, there's a process P1, there's a process P2, there's a process P3, process P4, process P5, and so on. Now assuming that process P1 wants to enter inside the critical section, and process P2, P3, P4 and P5, they are not interested to enter inside the critical section. Process P1 is interested, and process P2, P3, P4, P5, they are not interested. Now the processes which are not interested to enter inside the critical section, they should not stop any other interested process to enter inside the critical section same time, right? Or you can say, if they are not interested to enter inside the critical section, they should not stop the other processes to enter inside the critical section. That is called as progress. When we discuss about bounded weighting means no process should have to wait forever to enter into the critical section. There should be a bound on getting chance to enter into the critical section. So if any solution which is not following the bounded weighting, then there's a possibility of starvation. Let me tell you what is bounded weighting. Bounded weighting again is, assume this is a critical section and there's a process P1, P2, P3, P4, and assuming that process P1 wants to enter into the critical section, but all the other processes like P1, P2, P3, P4 and so on, all these processes are having higher priority as compared to the process P1. So if the process P2, P3, P4, P5, if these processes are not interested to enter into the critical section, the processes P2, P3, P4, P5 and so on, if these processes are having higher priority, then every time the CPU is going to allocate the critical section to the higher priority process, and the process P1 will always starve. That means P1 may not be able to get the CPU. So if P1 is not able to get CPU, when I'm saying bounded weighting, that means there should be a bound or weighting that at least how long, or you can say it, at maximum how long the process P1 has to wait to enter into the critical section. Or you can say there should be a bound on waiting for the process P1, that process P1 has to wait only this much amount of time. After this much amount of time, the process P1 should be able to get the CPU definitely. That should be guaranteed. Okay, that is called as bounded weighting. And the next is architecture neutrality. Architecture neutrality means there should not be any assumptions related to the hardware or the processor or the speed of the processor. So all the solutions which we are going to propose, those solutions should not be dependent on the architecture of the system. Those solutions should be independent of the architecture of the system. That is called as architecture neutrality. Okay, so these are the secondary conditions which should not be met. So every solution which we are going to produce or propose, those solutions should, you know, follow the primary condition first of all, and if they're not following the primary condition, then we are not going to check the secondary conditions. Secondly, if they are following the primary condition, then they should follow the secondary condition. All these four conditions should be met for a solution to be successful and a good solution. Okay, now let us jump into what is the synchronization problem.